Hello, everyone. Welcome to our next lecture on thermodynamics. In this particular instance, we are going to be reviewing a little bit before we move on. So I'd like to go over some of the equations that we've used so far for reversible and irreversible changes for thermodynamics. And keep in mind that all these changes are really just changes involving a gas where you squash it or expand it or heat it or cool it. There's no chemical reactions. And as a result, there's no bond breaking or bond making going on for these particular changes we're talking about. And a lot of times we're talking about monoatomic gases, gases from the noble gas family, argon, krypton, etc. To review them again, we've talked about both reversible and irreversible changes. I'm going to talk first about delta U, changes in internal energy. The changes in internal energy, of course, can be equal to another state function. Delta U is a state function. Delta T is a state function. So we can calculate delta U changes. They're changes in internal energy if we know the number of moles, the specific heat capacity of that particular gas at a constant volume. And since we have two state functions here, this equation, delta U equals NCV delta T, can be used for all conditions. Different pressures, different volume changes, you can use this equation. Now, if you take delta U and make it equal to QV, we have a state function equal to a non-state function. If it's this scenario, then we have to define the path. Just as we emphasized earlier, the analogy with the ski hill, if you want to make the elevation change equal to the distance traveled, you have to specify what path you want to take. So the path is you jump on the chairlift and you take the chairlift up. You're always going to travel the same distance, and you're going to the same elevation change will happen because you've defined the path. Same thing here. We know delta H, which is a special state function that's been created. Delta H's always happen at constant pressures because most conditions in a lab when we're doing experiments involve constant pressures. So delta H is always equal to NCP delta T. And likewise, we can use that equation for any scenario because there's two state functions in this equation. Or we can use it whenever we have a non-state function, heat. We can calculate it by specifying the path. And the path we're going to specify is at a constant pressure. Delta H's are always calculated at constant pressures. Another equation, delta H can also equal the change in internal energy plus any changes in pressure volume that have happened. And we can calculate changes in pressure volume by P2 V2 minus P1 V1. For reversible changes, note that the changes are, the formulas are the same. Again, because if we define the path, in this case, the path we're defining is it's reversible. So QV and QP, constant volume, constant pressure. Now let's talk about some differences here. So if we have an irreversible versus a reversible change, in an irreversible change, internal energy change, delta U, is equal to the heat and the work for that irreversible change. And we can calculate the heat by minus P external times delta V. In this case, the external pressure is different than the internal pressure, and the external pressure remains the same throughout. And whereas in a reversible change, remember in a reversible change, the changes are very, very small. For instance, if I was compressing a gas and I wanted to do it reversibly, I could take, for instance, a pile of sand and put it on a confined volume of gas, and then slowly increase the pressure to compress it by adding 1 grain of sand at a time. And that would happen very, very slowly and incrementally. And we can now establish that the external pressure and the internal pressure of that gas system that's confined are going to be equal throughout every single step. We can find the work by looking at the area underneath that curve. We can use calculus. We've derived this formula so that the work is equal to minus nRT ln V2 divided by V1 for an isothermal system where the temperature is not changing. And keep in mind that the work for a reversible system is different than the work for the irreversible system because, again, as I mentioned, the pressure external pressure is changing for the reversible change. It is not changing for the irreversible. Typically, you expend more energy during an irreversible change than a reversible change because there's wasted energy if you're compressing a gas. So reversible change, as I mentioned, the system pressure and the external pressure are always the same. Let's look at the curves here. And if it's a compression, which way is this curve going to go? Well, compression means that the pressure is going to go up and the volume is going to go down. So it's going to flow this way. When we find the work, again, we're going to use the external pressure to calculate the work. So if I'm going from state 1 to state 2, I can calculate the work done by the area underneath this dotted line because the external pressure is greater than the system pressure of that confined gas. Because there's such a big difference in that pressure, you get wasted energy. And we can find the work by minus P exterior times delta V for the work done for an irreversible change. Reversible change is different. In a reversible change, we're trying to find the area underneath that curve because external pressure and the system pressure are going to be the same throughout this entire change. To find the area underneath that curve, we are going to use some calculus. We're going to use very, very small little rectangles. We showed you earlier that you can then integrate and get the equation of work is equal to nRT ln V2 divided by V1. Different formula for reversible changes with respect to work. And keep in mind, the work for a reversible change is always less than the work for an irreversible change. Because like I mentioned, if the external pressure is much greater than the system pressure, you're going to have wasted energy. You're using energy that wasn't needed. The difference in those two is the energy that was saved if you happen to reversibly cause a gas to, in this case, the gas is going from a larger volume to a smaller volume, so it's being compressed. I'd like to talk a little bit now about spontaneous changes and entropy. We're going to be, for the next 2 lectures, talking about that. I'm going to talk about this little toy here is spontaneously just moving about. It wasn't moving until we wound up that spring. Once I wound that spring up, I let it go, and that toy from that point on will be moving. No additional input of energy is required. And that's the definition really for a spontaneous change. This is a spontaneous mechanical change. The energy stored in the spring is used to propel this little guy forward. Now let's consider some spontaneous physical changes. If I take a piece of ice and I put it anywhere in a room that's above 0 degrees, that ice is going to melt. No additional action is needed. The ice simply melts spontaneously above 0 degrees. Now, spontaneous change happens even though no external action is occurring. Once started, it continues going. I'll give an example of a spontaneous change would be hydrogen and oxygen blown up into water. And if you've ever seen this video, I'm not sure if you have or not, what I'm going to show you here is a little bit of this video. This is an old video from the Hindenburg. It spontaneously initially here These are spectators that were welcoming the Hindenburg, and all of a sudden the hydrogen in the Hindenburg burst into flames. It started reacting with oxygen in the air, and the hydrogen was burning and going up. Most of the fatalities occurred from the diesel fuel that was burning at the bottom of the Hindenburg. That diesel fuel was used to drive the fans that controlled the directions that the balloon was moving in. So terrible tragedy, spontaneous change. Once it started, it was believed it got started because of a spark that was generated somehow. So example of a spontaneous change there. So if I wanted to perform a spontaneous change with hydrogen and oxygen, I could just take that mixture of gas and throw in a little piece of platinum that acts like a catalyst, a surface on which those molecules will collide and stay there, and it increases the probability of the two molecules whacking into each other and releasing energy, making water. Now, non-spontaneous change needs a constant input or a constant action in order to keep going. The hydrogen burning certainly didn't need that. Here's another experiment where I can show you a spontaneous change. One of my favorite spontaneous changes. I used to do this in the classroom. You take a piece of white phosphorus and you dissolve it, kind of suspended in liquid carbon disulfide, which is pretty nasty stuff. And you put it on a piece of filter paper and you dip it in a mixture. And then you stand back, it starts to evaporate, and I'm going to show it to you here. So we call it the barking dog. There you go. High pitch, lower pitch probably happening next. There you go. Okay, so there's another example of a spontaneous change. Once initiated, it just kept going. If you wanted to go and search that yourself, I show you the YouTube location. Okay, so initially what happened was the CS2 kind of evaporated, and it was heavier than air, so it was sinking in that graduated cylinder. And then when the CS2, most of it was evaporated, the phosphorus is a unique substance in that it will spontaneously combust with any combustible material. So as it dried out on the filter paper, the phosphorus was exposed to the combustible material, the paper, and it burst into flames. And then as the paper burned, the CS2 gas also burns. So that's what you saw happening. It was burning at the top and then slowly burned all the way to the bottom. Very, very fun demo. So one of the less than pleasant things about phosphorus is it can be used in incendiary bombs to actually terrorize populations. It can land on the skin of people and actually ignite people. It's just a horrible, horrible substance to use for that purpose. Now, a chemical reaction is spontaneous because once it starts, it just keeps going. So some examples of spontaneous changes, everybody knows them. You burn anything, methane, wood, a ball rolling down a hill, a gas will fill an empty container, and heat flows from a hot body to a cold body. Those are all spontaneous changes. Ice, as we mentioned, will melt above 0 degrees. So here's another example of a spontaneous change I want to show you. The metal sodium reacting with chlorine gas. Just going to switch to my screen here. And here it is. It's queued up. Okay, what you see is the molten sodium reacting with chlorine. The chlorine gas was made by reacting hydrochloric acid in the container previously with sodium hypochlorite. Beautiful reaction, isn't it? And you're making salt from the sodium reacting with the chlorine gas. Love the glow. And that's what the remnant is that you see in my PowerPoint presentation here. All right. So to summarize, we lowered that molten sodium into the flask. The molten sodium reacted with the chlorine. Prior to the flask, the molten sodium being put in there, we had to get chlorine gas in there. You made chlorine gas by reacting sodium hypochlorite. Most people call it chlorine pucks. Well, the chlorine pucks really are sodium hypochlorite or calcium hypochlorite, which is this type of salt. They call them chlorine pucks, but they're not pure chlorine. They're obviously, the chlorine is in that compound. And if you react with hydrochloric acid, you get that reaction. NaOCl plus HCl produces NaCl plus H2O plus Cl2. And if you balance that equation, again, I'll talk about balancing equations very briefly. I always want to inspect it first and start with the substance present in the fewest places. Sodium is in 2 places. I can see it's balanced. Oxygen is in 2 places. I can see it's balanced. Chlorine is in 4 places. So I'm not going to balance it with chlorine yet. I'm going to balance it with something else that's present in fewer places. So I see hydrogen is in 1 place. There's 2 hydrogens on the right, but only 1 on the left. So I'm going to balance it. I can't change the formula because hydrochloric acid's formula is always HCl. It's not H2Cl, it's HCl. So I can only balance it by increasing the number of formulas. So there's 2 HCls, and now it's balanced. And that's how you can make chlorine gas relatively safely. Keep in mind, always do it in a fume hood because chlorine is very toxic. It causes chemical pneumonia if you inhale it, which means your lungs will fill with water. It'll form hydrochloric acid when it reacts with your tissues, which is corrosive and starts decomposing protein. Very, very horrible substance. I actually worked in a chemical plant as a student at Queens in the summers to make money to pay for school. Worked in a chemical plant, and I was exposed to some chlorine. Luckily, we had masks to protect us, but it reacted with my skin, and it felt like ants crawling all over my skin were biting me. It was a horrible experience. And then I had to leave the job site and go and take a shower after that happened because they didn't give us gas-proof suits. We simply had breathing apparatus, but we had to get this tank cleaned up quickly. So you had to endure that feeling on your skin for a period of time. Luckily, I was getting very well paid for doing it. Now, here's a cruise ship I just went on. You know, I wanted to treat my family to the best, so I picked a beautiful cruise ship. Here it is. Isn't that a beaut? Well, I want to use this picture just to show you another spontaneous change that's happening. And that's the rusting here of the hull of the ship, which is made primarily of steel. Main component of steel, of course, is iron. To simplify the reaction, it's way more complex than this reaction shows, but there's a simplistic chemical reaction showing you that both water and oxygen are involved in the oxidation of that iron hull. And another reaction that's actually a mixture of ferrous and ferric hydroxide, because the reaction of ferrous hydroxide continues and it makes ferric hydroxide. So rust is really a combination of ferrous and ferric hydroxide. It's not simply iron oxide that you might have been told that from a previous teacher who really simplified it a little bit too much. It's ferrous and ferric hydroxide, a mixture that makes up rust. Spontaneous process. Once it starts, just keeps happening. It's pretty slow. That's why if you keep substances dry, they won't rust. We all know that from experience. So some examples of non-spontaneous processes. A ball doesn't roll up a hill by itself. If I stop pushing a ball going up a hill, I got to continuously add energy to it. So it's obviously not spontaneous. Gases don't collect at one end of a container. They always remain dispersed evenly. So if I had a gas and I had kind of an entryway from one container to the other, and I open up this valve, the gas is going to flow from the left side to the right side. That's going to be the spontaneous flow. They don't go the other way. The gases don't simply, in this case, go from one container to the other and leave one of them empty. And heat does not flow from a cold body to a hot one. That's not a spontaneous change. Water doesn't freeze at temperatures above zero. It has to be below zero. It's not spontaneous above zero. Now, the direction of spontaneous change is often from a higher energy to a lower energy, but not always. We're going to talk about scenarios where the opposite happens. For instance, here's an example of an endothermic process. I don't know if you've ever used ice packs. I used to use them as an athlete to kind of help out a little bit when I was in pain from swelling. But here is an endothermic process. We take ammonium thiocyanate that's at room temperature. We add barium hydroxide octahydrate, which was also at room temperature. And when they are combined, it gets so cold, it actually freezes to a block of wood. So there was some water on that block of wood. When you lift it up, now it's now frozen. And if you felt it, it gets really cold. I used to do this in my classroom, and the fumes are not very pleasant. So you can see here that you can lift up all those books. That's how thoroughly frozen that was. All right. So returning here to our presentation, ammonium thiocyanate, ammonium ion, thiocyanate ion, a +1 ion, a -1 ion, barium hydroxide. Barium's a +2 charge. Hydroxide is OH1-. Going to need 2 of them. And there's waters associated with it. And just to keep it simple, I think it's an octahydrate, which means 8 waters. It's a very endothermic process. Why does it happen spontaneously? You might ask, if it gets so cold. If you only thought exothermic reactions were spontaneous, here was a spontaneous reaction that was endothermic. And can you guess why it's spontaneous? Well, think about it. The products that are formed are much more random than the substances that we started with. We started with crystalline solids here, made up of particles that were arranged in a particular way in crystals. And then we liberated them from their crystals into ions. The ions actually, the barium ion and the hydroxide ion, the ammonium ion and thiocyanate ion, which were stuck in crystal formation, were liberated into the water. And you actually make a solution of those 4 ions when you're finished that is much more random than the material that we started with. So that driving force, the drive towards more randomness, can sometimes drive a reaction to spontaneity. Now, a gas expanding into a vacuum, of course, doesn't involve an energy change. It just happens spontaneously. Entropy is what we're going to spend time talking about now. A simplistic way of entropy. Entropy is to simply consider randomness or disorder of a system. Entropy really has to do with probability states. And are there more possible states in certain scenarios than in others? And that's what entropy is. But a simplistic way of looking at it is to simply think of what happens to the overall randomness of a system. And a common thing to think about it is your hair. I know my hair certainly gets random over time. And certainly if I go outside or wear a toque, I get toque head, the hair just starts to go wacko. And I don't have any energy input in that. That just happens spontaneously. And similarly, my room and my house, I'm not the tidiest person. Stuff just gets dispersed over time. It just keeps getting more and more random, like the kitchen filling up with sink. The sink fills up with dishes all the time. Gets random all on its own. So there's a greater probability that a system will be more disordered than ordered. That's one of the laws of the universe. Entropy increases as randomness increases because the particles in a more random system have a higher probability of filling different locations. Now, entropy is a drive to a disordered state. Deck of cards is a nice way of thinking about it. So if you've ever taken a deck of cards that came right out of the box, they were ordered. They were all in suits. They usually start with like ace of spades, king of spades, queen of spades, and they go all the way from spades to clubs to diamonds to hearts or whatever it is. I'm not sure. I'll have to open up a deck to see. Well, it's highly ordered when you begin. What's the probability as you shuffle that deck and increase the disorder that it's going to end up back at the same state? There is a chance that it will, but it's a pretty low chance. And here is the actual number. If you calculate it, it's 8 times 10 to the power 67. That's the number of possible arrangements in that deck of cards as you shuffle it, which that number is greater than the number of grains of sand on Earth. That's an incredible level of disorder that deck of cards presents from that original ordered state. So there's the possibility that you're going to get a low probability state is very small. There's a much higher probability that you're going to get a more disordered state as you shuffle those cards. So the more disordered the state, the higher the entropy. The less ordered the state, the lower the entropy. So when you first got it, the deck of cards was highly ordered, has a low entropy. As you shuffle it, the disorder of the state of the system, in this case, the deck of cards, increases over time. So now here are some examples of some common changes that happen that result in a more disordered state. Switching from a solid to a liquid, melting things, switching liquids to vapors, boiling things, taking substances and dissolving them, like putting sugar in your coffee. The sugar solid breaks apart. The forces of attraction between the water molecules and the molecules in the solute are great enough to yank the particles apart. It is more disordered as a solution than it was as a solid and a liquid. A system at a lower temperature, if we heat it up, the particles move faster, they get further apart, or they get more random because they're moving faster. There's a much higher probability that those particles are occupying a more random state at a higher temperature than a lower temperature. So phase changes, dissolving, changing temperature, increasing temperature, all result in increases in randomness of states or entropy. These are highly ordered states. They're crystals. In crystals, the particles in the crystal are arranged in an orderly state. This could represent, for instance, a crystal of sodium chloride. Sodium ions and chloride ions in the ratio of 1 to 1. Highly ordered. Now, if we're left to our own devices, the crystals will suddenly break down over time. They'll fall apart. Look at sand on the beach. Those particles all came from rocks that were more ordered. Over time, energy from the universe, from weathering, breaks those particles apart and disperses them into a more random state over time. So that entropy is related to that state of disorder. When you remove constraints, you allow the molecules to move to more locations, they're more disordered, entropy increases. The second law of thermodynamics states that in a real spontaneous process, the entropy of the universe, including the system and the surroundings, must always increase. And this is the second law. Remember, the first law was the internal energy equals Q plus W. This is the second law. Entropy of a change will always, if it's spontaneous, will always go from the delta S of the universe will always increase. So a free expansion of a gas into a vacuum is an example of an increase in entropy. So we're going to define an entropy. In engineering, we need a macroscopic definition of entropy. In thermodynamics, delta S is a state function, and it's used to assist us in predicting whether a process is spontaneous or not. We'll calculate entropy change to decide whether it's spontaneous or not. We'll do that in future lessons. Now, to compute delta S for a system, we're always going to imagine a reversible path, because if it's a state function and it's equal to a non-state function, which is heat, then we have to define the path, and that path will be a reversible path. So delta S is a state function. Q is not a state function. So when we make a delta S dependent on Q, we are going to define the path, which is a reversible path. So you're going to hear me talk about Q reversible. So delta S equals the sum of all those tiny little changes in heat, dQ, that are absorbed or released. And then we're going to divide that by the temperature at which it's absorbed. And that is going to give us the change in entropy, delta S, for any system. It's the integral of dQ reversible divided by the temperature at which it happens. And we're going to calculate this for a number of different scenarios because we can calculate heat changes differently for different systems. So the first equation, there it is. When you're transferring heat to molecules, it makes the molecules move faster, creates more disorder in the system. This causes the entropy to increase. So entropy changes, delta S, are also dependent on temperature. So the temperature of a substance is high, it obviously has more entropy than the same system at a lower temperature. So to explain that to you, let's take a look here at a simple example. So here's our example. We have a gas A at a lower temperature and the same number of particle gas B. Sorry, this A is at a higher temperature, B is at a lower temperature. So we're going to say that A, the amount of internal energy of this system is 2,000 joules. And the amount of internal energy here out of a colder system is 200 joules. Because we know at a higher temperature, the particles are moving faster. They're going to have more internal energy than the particles at a lower temperature. They're not moving quite as fast. So if I add the same amount of heat to each container, add 2 joules of heat, let's look at the percentage change. So in this case, 2,000 joules went up by 2 joules, 200 joules only went up by 2 joules. So the percentage increase is the 2 joule change divided by 2,002 joules compared to 2 joule change divided by 202 joules. We can see there was 10 times more entropy change at the lower temperature than the higher temperature. So entropy changes are more significant for a system that is at a colder temperature than the same system that's at the higher temperature. Adding heat to a substance at a lower temperature has a greater effect. We're going to talk about isothermal reversible processes involving gases with no reactions, no bond breaking or bond making. In that case, if it's isothermal, temperature change is 0. Remember, delta H depends on delta T, change in temperature, and delta U depends on delta T. If delta T is 0 in both cases, then delta H and delta U will be 0. Remember, delta H is N CP delta T and delta U is N CV delta T. Again, both are equal to 0 for isothermal changes. So the system change, the delta S for the system, is equal to the integral of dQ reversible divided by temperature, which equals 1 over T. Because the temperature is constant, we can take it out of the equation, and we have 1 over T integral of dQ reversible. We know for an isothermal system that since delta U equals Q plus W and delta U is 0, that Q must equal Q must equal minus W. The work done on the system is equal and opposite to the heat. Now, Q reversible is a finite amount of heat absorbed during reversible isothermal processes. In order to keep the temperature constant, heat has to flow. Because remember, temperature is a measure of the average kinetic energy of the particles. This equation holds that delta S system equals Q reversible divided by temperature. There's our first derived equation. But we're going to derive this equation for different scenarios now. Delta S system is Q reversible over T, our first equation. But if isothermal processes involving reversible compression or expansion of an ideal gas, if it's a reversible process, it means it's being done in incremental small changes. In this case, Q, the heat transferred to the system, will equal minus W and we've derived this equation before. It equals nRT, the ln of V2 divided by V1. There's equation 2. Well, what if we substitute equation 2 into equation 1 for Q reversible? What if we say Q reversible is the same as Q for the system? And that way, we end up with, for Q reversible, we end up substituting in nRT ln V2 over V1. So we end up with Q reversible divided by T, which is now nRT ln V2 over V1 divided by T. Another equation. So delta S, in addition to equaling nR ln V2 over V1, can also equal nR ln P1 over P2 if it's the pressure that's changing instead of the volume that's changing. Both of those equations can be used depending on what you're given in the problem. So temperature, again, is constant in both of these scenarios. So non-isothermal reversible processes involving gases. For non-isothermal processes, the temperature changes. So delta S is going to equal the integral of dq reversible over T. If the process is adiabatic, we know what does adiabatic mean? It means no transfer of heat. It means the system is insulated perfectly. A kind of a theoretical thing. I mean, no system is insulated perfectly, but in order to calculate the change, we're going to assume it's as close to perfect as possible for these adiabatic systems. Heat is going to be 0. Now, if delta S, the entropy change, depends on heat, and there is no heat change, so delta S is 0 for adiabatic process. Easy peasy, isn't it? So if the process is a reversible isochoric, isochoric simply means there's a constant volume, then dq reversible equals du, the change in internal energy, because it's constant volume. Remember, a system that's under constant volume, energy flowing in or out of the system has to come from the molecules because the system is constant volume. It also equals NCV delta T because it's a constant volume. If the process is reversible isobaric, meaning constant pressure and it's reversible, then dq reversible equals dH, the change in enthalpy, which is also equal to NCP delta T. In this case, isobaric, meaning constant pressure, so the specific heat capacity changes. NCP delta T, slightly different quantity of energy for heat in this case. Now, if volume is constant, we're going to now replace that Q reversible term for a constant volume. So the Q reversible term can be replaced. So we get delta S is equal to the integral of NCV delta T over T. And we can, again, recognize it's an inverse relationship to temperature. So we can use calculus and the area under the curve again. We get NCV ln T2 over T1. Constant volume is the defined path here. So you can also use this, in addition to gases, you can use it for liquids or solids. So if it's a system that's isobaric, meaning a constant pressure, again, we're going to replace that Q reversible in our equation, and we're going to replace Q reversible with NCP delta T because it's a constant pressure. Isobaric, we get N, the integral of NCP delta T over T is equal to the change in entropy. Again, it's 1 over T here, so we can take that out and get the relationship, the ln of T2 over T1 times NCP. Area underneath the curve. We're going to integrate. You could use that as well for liquids or solids. So all these equations will be in your information sheet. It's important that you know where they are and how to use them. Now, delta S for changes of state. This is the first time in the course we've talked about changes involving bond breaking and bond making, isothermal changes. Now, what's an example of that? Melting. When ice melts, the temperature of the ice isn't changing. It stays at 0, which is why it's so effective at keeping your drink cold. Drop a piece of ice in a liquid, and the temperature of the ice stays at 0. The entire time it's melting, it's taking heat energy from the liquid it's in, and it's using that energy to undergo that phase change to break those chemical bonds between the water molecules that are stuck in those crystalline arrangements. And its entropy is obviously getting larger. It's getting more random as it melts. Liquid water obviously takes up a more random orientation than solid water. So again, we can calculate the entropy change for fusion is the integral of dq, those tiny changes in heat divided by the temperature of fusion, which equals, again, it's 1 over T. We're going to take that out of the equation. So we get 1 over T times the integral of dq, which we're simply going to express as Q reversible over temperature. And that happens at a constant pressure. When ice is melting, it's happening in the atmosphere. The pressure of the atmosphere is not changing over time, staying relatively constant for the period of time that the ice was melting. Now, QP, the heat involved, is equal to delta H, which is equal to the heat of fusion. And delta S fusion is equal to delta H fusion divided by temperature at which the fusion occurs. So for ice, that happens to be 273 Kelvin. Different substances have different melting points. So it's dependent on the material. When does that phase change happen? Delta H can simply be equal to QP, which we can simply measure with a calorimeter. Now, delta S for a vapor is the same thing, except now we're going to look at the enthalpy change, delta H, of the vapor. We're going to divide it by the temperature at which the vapor forms. If it's water, we're going to look at it at 373 Kelvin, 100 degrees Celsius, under 1 atmosphere of pressure. So it's the same for any state change, for any substance. And you'll obviously be given the temperature that those phase changes happen at, either solids to liquids or liquids to gases. Now, let's talk about another scenario here. If we have a change in the thermodynamic state between two separate situations, what if it's not an isothermal, adiabatic, isobaric, or isochoric change? How would you find the change in entropy, delta S? Kind of tricky, all right? In this case, if we look at this system, assuming we're going from here to here, what's happening to this system? Hopefully you can see that the gas volume of the system is increasing, the gas pressure is decreasing. Must be some kind of expansion going on. Well, if it's neither one of these four scenarios, can't we solve this? Because it's a state function, it's independent of path. Can't we define the paths and figure out the change in delta S by specified paths of our choice? That's exactly how these questions are done. All right, if we're going from state 1 to state 2, if it's a state function, it's independent of path. So we can simply figure out the change. If it's an expansion here, we can say, okay, well, what if we adiabatically change that substance? And then we go from one state to a third state. And then what if we take that substance and change it where the volume of the gas changes, but the pressure remains the same? So isobarically, we change it. Well, if we add the entropy change from 1 to 3 to the entropy change from 3 to 2, we have actually figured out what the entropy change is from 1 to 2 because it's a state function independent of path. So there's one way of doing it. Keep in mind, there's many different ways of solving these entropy changes, and you're basically left to your own devices to decide which path you want to take. But you're going to end up with the same answer regardless of the path. So if the first one is an adiabatic change, let's talk about the formulas we're going to use, okay? So the formula we're going to use, well, if it's an adiabatic change, it means there's no heat exchange. No heat is flowing into or out of the system. In this case, the gas is expanding. So as the gas expands, of course, it gets cooler. So heat must have flowed out of the system. But if it's adiabatic, heat can't flow out of the system. So it means delta S, which depends on, remember, Q reversible, heat. Well, if Q reversible is 0, then The adiabatic delta S is 0. But the change from 3 to 2, of course, is isobaric. If it's isobaric, what we're going to have to know is what was the temperature of the gas at the end and what was the temperature of the gas at the start. So we need to know T2 and T3. When we calculate T2 and T3, we can now figure out the entropy change from 1 to 2 simply by knowing what the change is from 3 to 2. It's going to be the same as it is from 1 to 2 because 1 to 3 is 0. That's one way. That's another way of doing it. Let's assume we could make an isothermal change from 1 to a new state, 4. And then isobarically, meaning at a constant pressure, we could change the volume of the gas. We could compress the gas isobarically. And if we add the entropy change from 1 to 4 to the entropy change from 4 to 2, we end up with the same quantity of energy as we found from 1 to 3 and 1 to 2 when we added them up. Or 3 to 2, sorry. 1 to 3 and 3 to 2 is the same as 1 to 2. 1 to 4 and 4 to 2 is the same as 1 to 2, to clarify. So 1 to 4 would be an isothermal change along this path. 4 to 2 would be an isobaric change along this path. So we're going to need to know what the volume changes are to figure out 1 to 4. And we're going to need to know the temperature changes if we're going to figure out the isobaric change. So depending on what you're given, this is another path you could take to calculate the entropy change from 1 to 2. A third way of doing it, we could isochorically, meaning we're going to cause a change in the gas at a constant volume. We're simply going to change the pressure of the gas. We're going to lower its pressure. That's 1 to 5. And then we're going to isobarically change the gas again from by changing, if it's isobaric, the pressure is not going to change, only the volume is going to change. So again, 1 to 2 could be calculated, the entropy change, by calculating the change from 1 to 5 and adding it to the change from 5 to 2. So for 1 to 5, we're going to have to know the temperature changes again. We have to figure them out. What's the temperature going to be at 5? What's the temperature going to be at 2? What was the temperature at 1? So if we know those temperatures, we could use this particular method of calculating the change in entropy. All right. Now I'd like you to pause this presentation and I'd like you to solve the problem in your course pack. The problem in your course pack is, I believe, on page 52. Here it is, the course pack. Okay. Page 52. There it is. Because you learn so much more when you do these questions on your own rather than watch me do it. So pause the video and try it on your own. Welcome back. Here's the question in the course pack. Calculate delta S, delta H, delta U, Q, W if 5 moles of argon expands reversibly at a constant temperature of 298 Kelvin from a pressure of 10 atmospheres to 1 atmosphere. What I like to do when I solve a problem is look for key buzzwords. If it's at a constant temperature, it means isothermal. It's reversible. Those are 2 important words. You're shown that it's a monatomic ideal gas is argon. So we know the value of Cp and Cv. Cp is 5 halves R, Cv is 3 halves R. That's useful information to us. All right. I've got highlighted here some of the key buzzwords that we're looking at. And let's draw a simple diagram. So if the gas is expanding, it's going from state 1 to 2, the volume is increasing and the pressure is decreasing. The pressure is going from 10 atmospheres to 1 atmosphere. But it doesn't tell us what the volume is. It tells us the quantity of gas though, number of moles. What can we do with that? Well, we know the number of moles at state 1. We know the temperature, we know the pressure, we know the volume, because we can use Vp equals nRT. We can rearrange the equation, V equals nRT divided by P. We can find V1, it's 12.2 liters, by substituting those numeric values in those locations. Let's look at state 2. After the gas has undergone its reversible expansion. We know the number of moles. We know the temperature. It's isothermal, same temperature. We know the pressure. We can calculate the volume. Volume is 122 liters. So far, so good. We're just using grade 11 chemistry here. First course in chemistry, if you weren't in Ontario. And we also know delta H and delta U are 0. Why? Because they depend on temperature. Delta H is NCP delta T. Delta U is NCV delta T. They both depend on temperature change. So if temperature change is 0, there's 0. Work, if it's a reversible change, it's an incremental change. It's very, very small. We're going to use the area under the curve, inverse relationship. So we're going to use ln of P1 over P2. We know P1, we know P2. So we can calculate the amount of work done, which is one of the things we were asking you to find. We can calculate the work is minus the number of moles times R times T times the ln of 10 atmospheres over 1 atmosphere. So P1 again is where you started. P2 is where you finished. Please don't get those mixed up. Most common mistakes we see are simply mixing up those two. And we want to change it into kilojoules from joules. And notice 3 significant digits throughout. So my answer will have 3 significant digits. So the work done is minus 28.5 kilojoules. And again, the gas is expanding reversibly. It's doing work as it expands. Work done by the system on the surroundings is negative. So Q reversible is going to be the reverse of that. So the heat required for that to happen, this is not an adiabatic change. It's an isothermal change. So heat can flow. So it's going to be equal and opposite to the work that was done, 28.5 kilojoules. Once we have the amount of heat, we can now calculate the entropy change. Delta S is Q reversible over T. Q reversible is 28.5 kilojoules divided by 298 Kelvin because the temperature didn't change throughout this process. We get 9.56 times 10 to the minus 2 kilojoules per Kelvin. Remember 3 significant digits, so I'm using 3 significant digits in my answer. Now, does it make sense that the entropy of the system is increasing? Think about it. Gas is undergoing an expansion. While when particles take up more space, as we discussed previously, there are more possible outcomes where the particles can be more random at a higher volume. So yes, it makes absolute sense that the entropy of this particular system is changing. So the gas is expanding. Second question in your course pack. 5 moles of argon at 298 Kelvin expands reversibly and adiabatically. So this one's adiabatic. It's not isothermal. Key buzzword, between 10 atmospheres and 1 atmosphere. This causes the temperature of the gas to drop. Then a second thing happens. The gas is then heated at a constant pressure back to 298 Kelvin. What temperature did the gas drop to in step 1? Take a look. So the entropy change for the system over the 2 steps also is going to be calculated. So here is the question with some buzzwords, important numbers and terms. We're going to highlight here. Here is a little drawing of it. So first, the gas expands reversibly and adiabatically between 10 atmospheres and 1 atmosphere. This causes the temperature of the gas to drop. The gas is then heated at a constant pressure back to 298. And that shows that change is going from 2 to 3. So how can I calculate the entropy change? Well, let's just put down some information that we have. We have at stage 1, we have 5 moles of argon gas. It's at 298 Kelvin. It's at a pressure of 10 atmospheres. We can find the volume simply by using Vp equals nRT. When we substitute those values in, we get 12.2 liters. Is the volume of gas at step 1. or state 1. At state 2, right here, after the first change has happened, after the first reversible adiabatic expansion happened at 2. We now know the number of moles of gas is the same, but we don't know its temperature, and we don't know its volume. Uh-oh. Little bit of a roadblock here. We certainly can't solve it using VP equals nRT. And now let's just talk about stage 3. Stage 3 in our transformation, number of moles of gas is the same. We know the temperature. Why? Because it does say that the temperature was 298 K, and the temperature, gas and heat at a constant pressure back to 298. It says the temperature was returned to 298, so it changed. We know the pressure at the end is 1 atmosphere, and we know the volume. We don't know the volume. Well, can we not find the volume in V3? Sure, we can. We can find the volume of V3 using VP equals nRT. So from the method 1 above, from 1 to 2 here, we can simply say the entropy change, if we want to find it from 1 to 3, which is what the question is asking, we can go in steps. We can find the entropy change from 1 to 2, and then add it to the entropy change from 2 to 3. Now, from 1 to 2, it's reversible in that adiabatic change, meaning no heat was flowing. Entropy depends on heat. If there's no heat, it's going to be 0. But 2 to 3, we need to know NCP ln T3 over T2 because it's an entropy change at a constant pressure. Okay. Sorry, not at a constant pressure. It's NCP ln from 2 to 3. Yes, 2 to 3 is a constant pressure. Sorry, just caught myself there. So NCP ln T3 over T2. We need to know T2. We can't solve it until we find T2. So that's a bit of an impediment. So we need to find the unknowns at 2. We need to find what V2 is, and we need to find what T2 is. Well, how can we find V2 and T2? Well, don't we know if we know P1 and we know V1 and we know P2, we have an equation on our information sheet for adiabatic and reversible systems. Woo, I'm relieved. Now I realize now the path we can use to solve this. We know P1 V1 to the power gamma equals P2 V2 to the power gamma. We have basically we have 3 of those quantities. So we could find V2 by rearranging this equation. V2 to the power gamma equals P1 V1 to the power gamma divided by P2. Right? There it is. So just grab that, get rid of it. And of course, we have to raise it to the power 1 over gamma to get rid of the gamma. We're going to raise it to that power. So V2, before we solve it, we need to know what gamma is. Gamma is Cp over Cv. Cp is 5 halves R, Cv is 3 halves R. You're always given that for in this case, it's argon, a monoatomic gas. That is given on your information sheet. We know gamma for this particular system is 1.67, and we're ready to solve. So 10 atmospheres times 12.2 liters divided by 1 atmosphere. The 12.2 liters is the volume. We raise it to the power of gamma, and then take the nth of 1.67 to solve. Okay. So we end up, when we do the math, we end up with 48.6 liters is equal to V2. So we've solved for V2, and that's going to help us. And now once we know V2, we can calculate T2 because we can use combined gas law, VP equals nRT. So this was the key right here to solving the problem, finding V2. So V2 gives us T2. And once we have T2, now we can solve for the entropy change because entropy change depended on NCP ln T3 divided by T2. We know T3 it's 298K. We can substitute in that equation now. We know there's 5 moles of gas. We know CP is 5 halves R. We know the ln of T3, 298, T2, 119. And we end up with 95.7 joules per Kelvin. The beauty of solving for entropy is you can select different paths. Now, at this point, you've answered the question. You don't have to go any further, but I just want to show you there's different paths we could take. All right. So, for instance, we could calculate the path directly from 1 to 3. I could solve that from 1 to 3 if I knew what V3 was. Because from 1 to 3, the path, which is isothermal, is simply NR ln V3 over V1, the change in volume, isothermal. So we have to find V3. Well, V3 is nRT divided by P. So we know what V3 is. It's 122 liters. So once we know that, we can calculate the delta S, the change in entropy, for stage 1 to 3. We end up, guess what? Same answer, 95.7 joules per Kelvin. Now, if for some reason you don't get exactly the same answer, it could be simply a rounding error when you're sticking numbers in your calculator. And, for this course in general, if you have a rounding error, a small, slight rounding error because you used the same long number with all those insignificant digits in it, you didn't bother to input that number in your calculator, I'm not going to hold that against you because it takes too much time for you to take numbers out, rewrite them, do it again. So slight rounding errors, I'm going to ignore as long as you use the correct number of significant digits. Now, method 3. We could simply say, okay, method 3, can't we calculate the change in state from 1 to 3 by simply going from 1 to 4, which is a change where the volume isn't changing, just the pressure is changing. So an isochoric change, and then adding it to the entropy change from 4 to 3, which is a change happening at a constant pressure. So isobaric, another way of doing it. So in this case, the temperatures have changed. So we need to find what T4 was. So we can calculate T4 again using combined gas law, Vp equals nRT. So V4 was 12.2 liters. And once we know that, we can solve 1 to 4, 4 to 3, entropy change, and we can add them up. And guess what? Same answer again when you do the math. Now, I would never ask you to do this 3 times. You just choose whatever method works for you. Let's compare our answers. So the first example, we went from 1 to 2 and then 2 to 3. 1 to 2 was adiabatic, probably should be a little steeper. My mistake when I drew this. And then at a constant pressure, we use entropy changes NCP ln T3 over T2. We knew the temperature changes. So the total for entropy was the entropy change for the adiabatic change added to the isobaric change. The second example we used was an isothermal change. So we calculated it directly from isothermally, figuring out P1, P3. One of them wasn't given. And the third way we did it was to perform a change where there was no change in volume, isochoric, and an isobaric change from 4 to 3. We know the temperature from T3 and T4. If we figure those out, we can then solve the problem that way. So 3 separate ways of solving the same problem because entropy is a state function. It doesn't depend on the path. So we can choose what path we want. Please go and complete the problems shown at the end of lecture 1.4 in your course pack. It is so important for you to do these on your own, particularly since it's new material you've never been exposed to. reinforce those brain connections by doing the work on your own, and then check your answers in Appendix B. If you made a mistake, then pore over that explanation and find out what you did wrong. And that is the most efficient and the most, I think, is the most productive way of learning the material in this course. So thank you very much. Here are some problems that you can do in Petrucci, the textbook, the first textbook problems I've assigned. So chapter 13, 1, 5, and 11. And then you can check your answers in Petrucci's answer book. Thank you very much. If you do have problems, feel free to contact your TAs. They should be making contact with you shortly. And then if you still have a problem, the TA couldn't answer your question, keep in mind there's almost 900 of you. If I had 900 people emailing me every day, I would grind to a halt. My progress would be minimal. So please, I will help you, but take advantage of some other resources first, all right? Particularly other members of the class. I'm hoping that you already have work groups from first semester and use each other as resources, use the internet as a resource, whatever is needed. So thank you very much and take care.